So key points, what are conductors, insulators, and semiconductors? Most of y'all should know that by now. How does current flow through conductors, insulator, and semiconductors? What are the key thermal, electrical, and physical characteristics of electrical insulators? How does light travel through materials? So what we'll do is we'll get a little bit of introduction into fiber, even though we have fiber in its own section. How is light contained in an optical? So basically we have two ways we can transfer information. So we use conductors for two different things. What do we use conductors for? There's got two functions in life. To carry, well, not really. That's not what I was looking for. You're right, though. They all carry current. Yeah, information or power. So we either use it for power, right, or information. A good analogy would be like the battery on your car. Those conductors are in there for power. And then if you look at, you got conductors running from your antenna for your radio. Those are not power conductors. Those are what? Signal conductors. Right? You understand? So our electrical conductors, or even our conductors, are going to either carry, our metal conductors are either going to carry power, or they're going to carry signals, or some of them carry both. Fiber only carries signals. So fiber optic carries signals. Fiber does not carry power. Everybody understand that? So, two ways power or information can be transmitted. Information, we can send it wireless, right? Either by using infrared or light, which is the two most popular, radio frequencies, or either ultra frequencies too. Conductors, we can carry information using metal or optical, right? Everybody okay? Terms, voltage. We already know what voltage is. Electrical difference in potential that causes electrons to move. We get voltage from static electricity. We get voltage from lightning. We get voltage from batteries. We get voltage from generators, right? Are we okay? Bioelectric, which is not listed. Current, the flow of electrons caused by a difference in electrical potential if we have a complete path. Resistance and reactance, anything that opposes the flowing of electrical current. Are we okay there? Let's try the other thing. Conductors, very often offer very little opposition to electrical current, has many free electrons, and that's what when free electrons mean, they're not actually free, they're just easy to move, right? You understand? So what we're trying to do in our conductors is we're trying to keep these atoms balanced. So what we do, of course, when we have a balanced atom or neutral atom, then the number of electrons you have matches the number of protons, right? So what happens is if we put a charge on one side and we cause these electrons to move, then automatically there's going to be another guy doing what? Falling in and taking his place. So all we're doing is we're just moving those electrons from one atom to the other. Free electrons means we got a lot of electrons in what they refer to as the conduction band. And these are elements that have one electron. Good conductors, the best conductors have one electron out there in that outer orbit. Right? And then that one electron that's out in that outer orbit, we can cause that to move a lot easier than if we have two or if we have three. The more we get toward 8, the more stable the atom becomes and the harder it is to get them out of there. And we'll look at that in a minute. Silver, copper, gold, aluminum, and etc. Aluminum is right on the edge of being a semiconductor. Aluminum has 3 in the outer shell. All our other conductors have 1. But what's the advantage of aluminum? So aluminum has more resistance than copper. But what's the advantage of aluminum? Cheaper and lighter. Yeah. With silver being the best, followed by copper, followed by gold. So what advantage does gold have over other metals? Huh? No, that's the order right there. Copper's a better conductor than silver. I mean, than gold. So what advantage does gold have over silver and what over copper? Why do we coat stuff with gold? We very seldom use gold as a conductor. We usually use gold as a plating. Why? Yeah, it doesn't corrode, or it doesn't corrode that we understand corrosion. You know, they pulled up gold out of the ocean, and the ocean, salt water is very corrosive. They pull money out of the ocean that's been down there for years, and it still what? Still looks like almost like it did when it went down there. So anything that we're going to expose to the atmosphere, copper oxidized or rust easy. Copper rust. The problem we have with copper rust is that it's an insulator. Copper rust is an insulator. Silver rust is as good a conductor as silver. But the problem is silver is very expensive, right? You understand that. And then if we oxidize and that silver rust starts flaking off, that's going to give us problems too. So usually silver and gold we use as a plating. So contacts are these switches where we're basically making a circuit by bringing two conductors together. Well, what they normally do is out here on this place where they make that connection, what they do is they'll silver plate that. So if you look at a relay contact and it's gray, don't clean it off. That's just silver that's oxidized, right, or rusty. So anything, usually copper, if we're going to expose copper to the atmosphere and we're concerned about that thing, then we'll coat it with gold. Tin's becoming a very popular coating for things that have a short lifespan. Tin will oxidize, but it takes it's got a real high oxidation level. It takes longer. Originally in computers, they used to gold plate everything. All your connectors and everything were gold plated. Now you'll see a lot of tin plating inside computers because computers have a limited lifespan before you get rid of them. Few hundredths of an ohm per 1,000 feet. Insulators offer extremely high positions of electrical current. Few free electrons, rubber, plastic, fiberglasses, Teflons, millions of ohms per inch. So there's no such thing as a perfect insulator. If I put enough of a potential across anything, there's going to be current flow. So there is current flow through the insulator of a conductor. But it's so low that we don't have the ability to measure. Semiconductors fall between conductors and insulators. To be balanced, and this basically explains it, to be balanced, an atom requires 8 electrons in its outermost shell. And what's so strange, if you took chemistry or biology or any of those things where they talk about atoms, you'd start off with a maximum in 2 in the first shell, and then it would start changing, and every shell would get more atoms, except the outside shell could always have it's got to have at least 1, but it can only have a maximum of what? 8, period. And this is referred to as the valence shell. So no matter what atom it is, that outer shell has got to have 1, unless we move it, and then what? Maximum 8. So this is what defines the conduction characteristic of the atom. Elements with atoms that contains 3 or less electrons in the valence shell easily shed these electrons when acted upon by outside source. So these guys fall into the category of conductors. So if we looked at a periodic table that lists the shells, I don't know if I've got one in this PowerPoint or not. No, I'll show you that. But if we looked at the periodic table that lists the electrons in the shells, every one of these, silver, copper, gold, would have 1 out there. But when you look at aluminum, it's going to have 3, which basically barely fits into the category of what we call a conductor. These elements make good conductors. It should be obvious that elements with 1 valence electron make the best electrical conductors. Most metals fall into this category. Didn't say I always said what. Where do I have that periodic table at? Oh, I know. We teach this in more detail in a solid state. But just to pop this up to show y'all that. I don't know if y'all can see this or not. But here's our conductors right there. I know it's hard to see. But this is the layout of the shells. Can y'all see what that says right there? It says 1. That's the valence shell. This says 1. This says 1. This is copper. This is silver. This is gold. And this is another. It's a gaseous or real soft metal that we can't use. Can y'all pronounce that? And here is aluminum. And I've covered up the chart. There we go. And this guy right here, can y'all see what that says? 3. So aluminum is barely in the category of what we consider a conductor. So y'all see that again when you take solid state. If you take solid state is a requirement in the ILT, but it's not a requirement in the AUT. I don't even know. I don't think it's one of y'all's electives, even though it's a good class. Elements with atoms that contain 5 to 8 electrons in the valence shell want to retain these electrons. Materials that fall in this category make good insulators. Of course, the one that has 8 would be the best, right? Understand that. Since the insulators do not want to give up any of their valence electrons, the amount of current is greatly limited. Elements with 8 electrons, valence electrons, make the best insulators. That makes sense? And I've already stopped my slide with my PowerPoints. So we could find the best insulator in the periodic table. What we would look for is ones that had 8, right? But these are going to be your rubbers, right? You understand? Semiconductors are elements that have 4 electrons in the valence shell. Natural semiconductors are carbon, silicon, germanium, tin, lead, silicon and germanium are the 2 most widely used. Now what we do with these is we deliberately, we call it impurities, but what we deliberately do is introduce other atoms into the lattice or matrix or the crystal to control the characteristics of these. This is called doping, by the way. Semiconductors can be used to control current flow with a very small applied current. These are BJTs. Control current flow with the applied voltage. These are FETs. So BJTs and FETs, these are current valves. Y'all know what valves do? What do we do with valves? Water valves. We control the flow of what? Water. So we can use these things as switches. We can use current. We can use one lead to turn these things on or turn them off, or we can use them as kind of like rheostats, but they're electronically controlled rheostats, where we can precisely control the amount of current that gets through the valve. Control the direction of current flow. These are diodes. So diodes are what we use to convert AC into DC. Produce light. Everybody's seen LEDs. Right? These are light emitting diodes. Receive light. These are photodiodes and phototransistors. Thank goodness, that's so cool. This is what makes your remote on your TV work. So on one side you got a light emitting diode, and you're shooting that into a phototransistor that's picking up that light, right? Which is pretty neat. We can use these to produce a voltage. These are photovoltaic cells. Most people call these solar cells. These are what we can buy to charge batteries up and all kinds of stuff with solar cells. We can make them sense pressure. We can make them sense temperature. So this just doping of this semiconductor, we can use these. This is electronics. Semiconductor is electronics. Because look at all the different things we can do. And then we got down at the bottom, we got and more. So just be some that y'all are familiar with. So we can make it amplify signals. We can make it convert signals. We can make it control flow. We can make these computers. We can use these make switches, which is what this computer consists of. Light principle. These are electromagnetic waves that move through a vacuum. AC flowing through a conductor emits electromagnetic waves. A lot of people don't know that. Light is an electromagnetic wave moving at a much higher frequency than an AC current. So if we could see a wave of light, it would look just like a sine wave. But is it moving at an extremely high frequency, right? You understand? Material will either pass light easily. We call these what? Transparent. Pass light with difficulty. We call these what? Translucent. Or block all light. We call those what? Opaque. Y'all heard those terms before, right? Refraction. The bending of light as it passes through material that conducts light at different speeds. Have you ever witnessed that? When? Where? Anybody's ever had a fish aquarium? Or gone? Anybody ever gone fishing? You never gone fishing? In a real nice clear water, you see the fish down there. If you ever did bow fishing, you become very good at this. If you shoot where the fish is at, where you see them, they're not there. Because what happens is light travels at a different speed through water than it does air. So what happens is the light, when it hits the water, bends. So the fish are not where they look to us because we're seeing them at a different place than where they're actually at. And this is referred to as refraction. It's the bending of light when we pass through materials that's got different indexes of refraction, is what we call it. And if you ever had a fish aquarium, you'd know that. You got on the top, you saw your fish, and you look down at the bottom, you look at it from this side, they look different when they're up at the top, right? When you look down at them, because of what? Because of this thing called refraction. Attenuation, the loss of signal over distance. This is also true for attenuation is a term we'll use in this class. So normally when we say a conductor has a certain amount of attenuation, that's a loss of signal over distance. Caused in electrical conductors, that'll be because of the resistance of the wire. In fiber, it's going to be basically because of the resistance of the material we're trying to send that through. It's almost impossible to get something that is truly transparent. There's always going to be some type of impurities in there, right? So fiber optics carry very little energy, only used to transfer information because of high frequencies can transfer enormous amounts of information. And the big thing is it's not affected by electromagnetic interference. Y'all understand electromagnetic interference? Yes, no? Are you okay? Well, what happens is we don't have it here. If we was over in the motor control lab, it is used. So what we got over in the motor control lab is we got this big magnet. And then what we'll do is we'll take a wire and we'll just move it to the magnet. And you'll see a voltage being generated in those wires. What happens is anytime we pass a magnetic field through a conductor, it induces a voltage into that conductor, whether we want it to or not. So we call this electromagnetic interference. You can see this. Let's see if this guy's plugged in. It's wrapped around it. I don't know what that's. Y'all guys take a 2-minute break while I get this sorted out. Yeah, I made 2 Ds when I was in college. One was speech, believe that or not. Another was English. 101, 101. I made a B. I made an A in 102. But she. I had the same thing happen to me, so they better not. But she made me read mine. And the English teacher, I took my English at Jeff State. And when I started working at here, that same English teacher was teaching me. Frankie Hitchcock. Dr. Frankie Hitchcock, but I could call her Frankie. Anybody else called her that, she'd get upset. This is, let's see if this works. If people don't understand the type of stuff that's literally floating around in the air. So we got all this electromagnetic interference around us right now. And thank goodness. If I wasn't picking up a lot of electromagnetic interference, guess what wouldn't work? That touch screen wouldn't work. We got several methods we can develop a touch screen. We can use what they call a resistive touch screen, which basically has 2 plates that's together, and when you press them, it's got a center thing in it, and you change the resistance. Those is really nice because you have to press on them harder. You won't run into these guys in like manufacturing and stuff like that because you're a very harsh environment. So most of your HMI panels that you run in the industry uses a variable resistive touchscreen. So you can push on them. But what's nice, you can have gloves on and push on them. You can hit them with your fingers. These guys works off the voltage that's being induced into my body. These guys use little capacitors, and these are called capacitive screens. So what happens is they have a matrix of thousands of little things like this, and when you touch it, it uses the interference on my body that's in my body right now, just strictly because EMI being induced into my body to trigger these guys to indicate a location. So this is why these you hit them with your fingernails, they blow up. Don't work. What is it, Hotel Transylvania 2? I watch those movies, they had grandkids. Oh yeah. And the old Dracula's they give him a phone. He's got this big old long fingernail and he's trying to tap something. He can't tap anything because he's hitting his finger. But these, if you got gloves on, they don't work, right? You understand? Because why? They work off this capacity. Because they're special styluses. They're set up to emulate these. So you can get some rubber stylus. So this guy right here will work on this guy. And all it is a stylus. I don't have it hooked up, but it won't work on my phone. So it's the principle of operation, the way your touchscreens actually work and how they pick up stuff. So that's what's nice. So I can take this and put this up against mine all day long and it don't do anything. But yet I got a stylus at home that works okay, but it don't work. You still got to press on it a little bit. So that's a good question. So if we went over to the HMI panel over there on the manufacturing line, So this is electromagnetic interference. My scope picks it up. This is me. This is what's making the touchscreen work right here. It picks up this signal from me. And it does it in metrics, and it figures out where my fingers are. You see that? Of course, our predominant one, it's a lot of frequencies in there, but our predominant one is 60 cycles. So not only do you see the 60 cycle, but also you see that ghost thing. So right now I'm picking this up. I'm just standing here, and I'm picking this up through what we call electromagnetic interference. So when these magnetic waves fly through my body, it induces a voltage into my body. Now the problem we have with signal wires, we don't have problems with EMI on power wires because they're conducting a lot of current, right? It's hard for electromagnetic interference to induce something that's got a lot of current there. But in signal wires where we're dealing with high impedance loads or high resistance loads, because we're not trying to send power, we're trying to send signals. So the circuits are high impedance, and these guys are the guys that we have to really worry about EMI. Fiber optics, no such thing, because it's electromagnetic induction. Light don't care. So one thing nice about fiber optics is they are impervious to electromagnetic interference. These guys, we gotta do something. We gotta do special things, right? It limits the amount of distance it can run. It limits how we can run them. You never run signal wires in parallel with power wires, not unless you separate them by a great distance, right? Understand? So this is why if you look on a power line, the power lines are up here and the cable TV lines down there about 12, 15 feet, right? You understand? So it gets out of the range of the electromagnetic interference. But if you're running, we had this, you know, I worked for a scale company for a while, and we had some very good conversations on people wanting to dig a ditch and run the power to the scale and the signals, the lighting and everything in the same trough. And I said, you know, you can't do that because your scale will be crazy. Your scale will go crazy. So in signal wires, this is where these EMI gets us into trouble. Wires that are, and we'll see how we can illuminate that or make it negligible with the type of cabling and stuff we do now. And this will make sense later on why we do things the way they are. Why when you take that thing apart, you can't untwist those wires. If you untwist those wires, then it's going to pick up a lot of EMI. If you do twist them, then it'll have the right impedance and you get the loading and everything that we need. So we call these twisted pair cables, and you'll understand why they're twisted. And so one of the things we're going to do is learn how to build. One of the things you're going to do is learn how to build those cables, how to wire them correctly, how to color code when you come up here and hook them up. And understand why you have to maintain those twists, and why you have to do this, and why you have to do that. Why coax cable? Why do we have to do this? Why do we have to do that? And why can't you just twist wires that communication cables? Why can't you, if you got a break, why can't you just twist the wires together? You have to splice them properly, or you're going to have a problem. Oops. I can't do that with the screen. The screen won't let me switch the screen. So electrical conductors can carry power, they can carry information, or they can carry both. Far less expensive than power systems, but subject to capacitance, inductance, and electromagnetic interference. Anytime we're sending a varying signal, this is a signal that varies, then we got to worry about these things we call capacitance and inductance. DC, we don't have to worry about capacity and inductance, but we got to worry about EMI. Terms: attenuation, cladding, conductor, core, corona, critical angle, dielectric. We're going to kind of skip over the fiber stuff, most of the fiber stuff, because we have a whole section of 4 weeks on fiber. So here we'll probably deal with mostly on copper. So conductor current flow, Ohm's law, conductors and semiconductors equivalent circuit. So what we have to understand is, number one, what E. So this book, I got this out of, and this is the way I learned it in the military, is that we learn E as what they refer to as an electromotive force, or voltage as electromotive force. Or what we refer to as an EMI. Now, a lot of people use this because I calculate I, but what's I? I is in amps, right? I calculate ohms, right? If I calculate R, it's going to be in ohms. But the way we teach it, I calculate voltage, it's going to be in volts. What's the problem with that? You got V on both sides of the equation. So a lot of people don't like that. They want the unit to be different than what you're solving for. So you'll see this used a lot in books. Instead of using V for voltage, they use E for voltage, which stands for electromotive force. So you'll see formulas that says E is equal to I times R. So here you got E, which is what you're solving for, and your units are going to be in volts. So what we got voltage is equal volts, right? You understand? So you'll see this a lot. So this book that I got this out of, they use E to represent what? Voltage. But E stands for EMF, which stands for electromotive force, and you can understand why they use that. So when I learned electricity or Ohm's law in the Navy, we learned E. And so you'll see a lot of books use E, and you see a lot of books use V. Basically, most of our textbooks that we use here use V for voltage, and they use V for volts. Are you okay? And it don't confuse anybody, but you can understand that. So here they're saying, okay, anytime I put current through a conductor, that conductor is going to drop some voltage. And why is that? Because all conductors have an R. Now it's not much. It's usually rated in so many ohms per 1,000 feet, but it's still R. If I put current through an R, it's going to drop a voltage. And if it drops a voltage, it's going to release power. So these conductors get warm. Right? You understand that? So what depends on how much voltage we have. And so this is the equivalent circuit. Even though the R is very, very small, this is the equivalent circuit of a conductor. This is not the load, this is the conductor. Right? You understand that? So what determines the resistance of a conductor? A metal conductor. We'll harp on that all semester long. What's that? Okay, the size. Length. Material. Somebody said that already. And there was some before. Well, sorta. It's actually the temperature. But the insulator affects the ability of the conductor to get rid of the heat that's being generated by the conductor. So this is why NEC people don't understand this. So they rate the ampacity according to what insulator you use, because that insulator determines how easy that conductor can do what? Get rid of the heat. It's just like us out there. It's getting cold. What do we put on? We put on insulators, right? You understand? And what does that do? Well, that reduces the ability of our body to get rid of heat, right? In the summertime, what do? We start taking it off. We take the insulation off, right? So, insulator current flow, and what we have to understand is that the insulator has current flow through it, and that's what a lot of people don't understand, because there's no such thing as an infinite R, and I is equal to V over R. So if I don't have an infinite R in my insulator, and I put a potential across it, that will be current flow through the insulator. Y'all understand that? So what this does, it actually sets up a little device called a capacitor. So the outside of the conductor acts like one plate, and the conductor itself acts up another plate, and this creates a capacitor. Now what that means is that the current flow in the insulator and the current flow in the current flow in the conductor are out of phase with each other, and they're about 90 degrees out of phase. So it means what that means is when this guy here is maximum, the other guy right here is going to be minimum. This guy starts dropping down, so they're actually out of phase. And that's what they're trying to show. Are we okay? So this is the actual equivalent circuit of a typical conductor. This would be the R of the conductor. This would be the capacitance of the conductor between the insulator and the actual conductor itself. So this would actually be the current flow in the conductor relative to the current flow in the resistor. This is not a formula y'all got to know, guys. It's just to give us a little bit. Scared you, didn't I? So this would be I in the conductor, E, the capacitor, E would be the voltage, and it would be at an angle of 90 degrees. And then we'd have to use this formula that we looked up the other day, and this is nothing that we have to know. All I want you to know is make sure you know about in this class is there is current flow in the conductor. Now in the insulator, what determines the amount of current flow we have in there? Well, not the conductor, in the insulator. What would y'all think? What was some of the things that could affect that? Well, that would determine, right, it would be what? It would be the size. It would be the what? Material. It would be the what? Length. Would be the temperature. And then, of course, we would have to add another one. I don't know how to phrase this. Contamination. So the problem we have with insulators is they're exposed to what? Elements, yeah, and they get dirt on them, they get all this kind of other stuff on them, and that would affect current flow in the insulator too. So you got these cables that spin out a long way. That's why a lot of times we'll protect a wire, we'll protect the insulator with something we call a jacket. So we're going to learn two terms. An insulator is in there to keep that voltage inside that cable. Because it's looking to get out, right? You understand? And then we got something we call a jacket. A jacket is a coating that we put around things to protect it against the environment. So the jacket is not intended to be insulated. And that's not exactly true. Sometimes the insulator and the jacket are the same thing. But a cable, a true cable that has two or more conductors inside of it, the conductors will have their own insulator, and then they'll be encapsulated in another plastic sheet that is truly a jacket. And that jacket is not an insulator. That's in there to do what? Protect that cable against the environment. So what's the main function of the insulator? To keep the push in. What's the main function of a jacket? Protect the insulator from the environment. The capacitor is created when two conductors are separated by an insulator. Virtually all the electrical current exhibits capacitance. Electric capacitant currents leads the resistive currents by 90 degrees. X of C is determined by the material length, thickness, surface contamination. So this, did I spell contamination? I don't think I did. I was thinking about it. But this is the problem we have right here with the insulator or the jacket. Not necessarily the jacket, but if the insulator is exposed to the atmosphere, right? Or exposed to contamination. Approximately 100 times greater than IR. We don't need to know that. But this is what we do need. So this is the name given to the current that flows through the insulator. It's called what? No, the name of the current. The name of the current. Volumetric current. So that's the name technically given to the current flow through the insulator. And then the current flow across the surface, which is caused by contamination, this is pretty straightforward. What's that? What we call that? Surface. Of course, R of the insulator is much, 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 much greater than the R of the conductor. Everybody understand that? R in the insulator is called volumetric current. The surface current is called the surface current. So we got three current flows, right? What's the three current flow going on the conductor? We have the current flow in the conductor. We have the current flow in the insulator. And then we have the current flow on the surface. And of course, the current flow, luckily, the current flow, and we can get a lot of contamination. In the old days, before we do a lot of things, I don't know, we used to have spark plug cables. We had an old, if you got an old car, you might still have that. So what they did, the timing of the spark plugs, is we had this, what we call a distributor cap on there. And what it literally did, it had a rotor in there that just went around and hit buttons on the inside. And we had no suppression or anything in our spark plug cables. But what would happen when they started to get a lot of surface contamination, since the insulator went in the top, what would happen to your cables? Anybody remember? The car would start missing, and that still happens. The car starts missing, right? And you go out there at night and you look and you see it's arcing through the wires. Well, that was originally started probably by surface contamination. The problem is once it arcs, it creates carbon paths right through the insulator, and then it'll arc all the time. And the only option you got is to, of course, most spark plug cables are really hard to get to now, but it was always a good idea to clean your spark plug cables every once in a while. And we don't need to know that. That's Pythagorean theorem, by the way. You'll run into Pythagorean theorem in that. IT is insulator is predominantly capacitive. The insulator goes IR trends to increase and IC increases. This can be tested, but we have to have special test equipment to do this. We can check we've got a meter where we can check the resistance of the insulator. So we call it a megometer. You ever heard of one of those things? What it does, it puts out extremely high voltage, because a regular meter will not check the resistance of an insulator. We'll look at that later. So this is nice enough stuff. Electromagnetic waves, and this is, we'll deal with this a little bit, are extremely high frequency. Light frequencies are anywhere between 1 times 10 to the 14th slightly to 1 times 10 to the 15th hertz. Y'all understand that? Those are big numbers, right? Yeah. The visible light that we can see, basically runs from about 4.29 times 10 to the 14th up to 7.5 times 10 to the 14th. For an example, though, FM radio, the FM radio range would be down in megahertz. So that's what you're doing when you're tuning your radio. You're tuning it to. We talk about carriers in this class just a little bit. Did we talk about carriers in this class? What class did I talk about? What we do, we have a technology. We refer to it as multiplexing. Have you ever heard of multiplexing? What is it? Yeah, multiplexing is when you allow more than one signal to share the same medium. What's medium? Media. What is media? Huh? Could be wire. Media is what information flows through. So right now, what medium am I using to send you information? I'm using air. So air is a medium, right? We could use conductor, fiber, could be media. So anything the information comes through. If we allow multiple signals to share the same media at the same time, or share the same media, we call that multiplexing. We got one form of multiplexing, which is what Ethernet uses. We call it baseband. I don't know if y'all heard of baseband, but baseband, the way it works is you only let one device occupy the media at any one time. So you put it, a device gets access to the media, it comes off, another device gets access to the media, another device. So that's called baseband. That's what Ethernet uses, wired Ethernet. We have another thing that we call broadband. What's broadband? Y'all hear that all the time. Broadband. What is broadband? Well, it's multiplexing. But broadband is where you let multiple devices share the same media at the same time. So we're definitely broadband in here, because how many devices are sharing our air right now? A lot, right? What's nice about baseband is when the device is on the network, it gets the total bandwidth of the media. When you do broadband, then everybody shares the bandwidth of the media. So it means everybody gets on the media, but they have a narrower bandwidth, right? Does that make sense? So what we do to do broadband is we have to modulate the signals. Modulation means we put that signal on another high frequency signal. We modulate it. Y'all have heard of FM? What does FM stand for? Frequency modulation. So what we do is the signal itself changes the frequency. The information changes the frequency. Then we have what we call AM. What's AM? Amplitude. AM changes the amplitude. Now, why is AM popular? Because EMI affects amplitude. So that's why AM was so dang noisy. It hums all the time. All right, you turn your radio on AM, and it's constantly doing what? Because it's picking up outbound power, right? FM, it's hard for EMI to change the frequency. And then what we do is we have special circuitry that we can bring this into. We call them tune circuits, where we can strip that carrier off. So we use the carrier so we can put multiple things on the same place at the same time. And then we do what? Then we bring it into a tuned circuit, and then we do what? We strip that off. So that's what you're doing on your radio dial when it says 97.3. That's the frequency of the carrier. So what you can do is you can tune your circuit to the frequency of the carrier, and what does it do? It ignores everybody else. All these guys are still there, so your antenna out there is picking up everybody. Your antenna is picking up these guys, your antenna is picking up all these radio stations out there, but you got the ability to go on your radio and set up a tuned circuit, and what it does is it passes that carrier, right, you understand, and does what? Blocks everybody else. And then we electronically strip the carrier off. We strip the carrier off from the signal, and then we get the signal into our radio so we can turn it up and down. So modulation or broadband. So I'm down at Jordan-Hare Stadium or Denny Stadium on the 50-yard line. There's 75,000 people up there, and I'm trying to listen to my buddy up there. That is multiplex. That's broadband. But all I'm gonna hear is what? Right? Unless I got the ability to do what? Tune everybody out. So that would be like you're out there and you pick up your cell phone and you call your buddy up on the stand and you put it up against your ear. Well, you just demultiplexing, right? So multiplexing is the act of putting something on a carrier. We call that modulation. And when we strip it off, we call it what? Demodulation. Does that make sense? And we call these devices that can do both, what do we call them? Modems. What do you think modem stands for? Modulator, demodulator. So that's what allows your computer, your modem, to be on there at the same time that all the other computers are out there. Because your modulator is set up to modulate your frequency on there, and then it takes something coming back to you and does what? And demodulates. So y'all know what a modem is. So that's what you're doing on FM is you're tuning in the frequency of the carrier. you do the same thing on AM. What's nice about FM is you're looking at the frequency of the carrier. Most radios, if you put it like on 93.7, most of them will put a little MH out there, which stands for what? Megahertz. Your TV is modulated too, but what they've done for TVs is they give you a channel number. But you set up a tuned circuit to let a carrier come through. You can look up those channels. They'll give you the carrier. You can look up the channels, and every channel has a certain what? Has a certain carrier. But instead of us learning all those carriers, they just assign that new carrier what? A number. So visible light, we can modulate light too. I mean, if we can modulate light, then what can we do? We can send information with light. And that's what we do with fiber optics. We modulate the light. So this is electromagnetic waves. So your remote on your TV is usually where? Yeah, it's usually an infrared. And infrared we can't see, right? You know what I'm saying? So that's why you can take it. Some cameras will pick it up. I used to have a camera that would. It was real neat. I could take my remote and put it up here, and you can see it flashing. But some cameras, some cameras on phones will pick it up. My iPhone won't pick it up. Some of them can, because a lot of your cameras now do auto adjust for the light. It's pretty neat. So infrared, we do that. That's invisible, right? So this is the other thing. Normally, fiber optics, we operate it down in here. And then we operate it toward 13, down in around the 850, 860 nanometer range. Did you hear what I said? Where did that come from? Well, what we do on light is we don't give the frequency in fiber. We give what we call the wavelength. So the wavelength, it's just like the ocean coming in there. If it's coming in, it's kind of like AC, right? Where there's a link there. You have a frequency of the waves, but then you have a link between those. So when Alabama Power is generating a waveform, it's moving down that cable, and each one of those positive alternation peaks they're a certain distance apart, right? Y'all understand that? So in light, we have wavelengths too. So normally in light, we don't give frequency, especially in fiber optic cables. Fiber optic cables are rated at what we call a wavelength. And that would be the spacing between the tips of the waves, right? You understand that? Now, the way you calculate wavelength is determined by the frequency of the wavelength relative to the speed of light. A light is moving at 3 times 10 to the 8 meters per second. So this is what we do to get it into nanometers. We take our answer and multiply it by 9. And this is going to convert it into nano, right? You understand that? Okay? So what I do is I take the frequency that I want to convert, I divide that by the speed of light, and then I multiply that by 10 to the 9th, and then that'll be the answer in nanometers. Y'all understand that? Yes or no? So when you buy a fiber optic cable, or when we talk about fiber, they're going to give the light that system is designed to handle in what we refer as nanometers. So what would be, this would be around 800 nanometers, right? But if we went back to the frequency, they're going to give us the frequency. So these are in frequencies. But what would we do if I wanted, let's say 4.29. So how would we convert that over to a wavelength? So my wavelength, which is abbreviated by the symbol lambda, would be equal to what? Yeah, so it's going to be what? 3 times 10 to the 8. Right? Meters. Okay? Divided by the frequency in hertz. Are we okay? So how would we do this? I'd say what? 3 times 10. So your calculator has an EX or EXP or something like that. That stands for times 10, right? And then I'd say to the 8, right? You okay so far? Then I'm going to divide that by what? My actual frequency, 4.29 times 10 to the 14. And then I come up and get that huge number right there, right? Then I'm going to multiply that times, oops. Then I'm going to multiply that times what? Times 10 raised to the 9, and that would be 699 nanometers. We should be where? It's going to be down in infrared, right? Usually fiber optics we use, I think 830. 830 is a very popular one, which would be, you could actually see that. So y'all want to do this one right here, just to see if we got it? So if I gave you this formula, would y'all be able to do this? Yes? This is lambda. That's the symbol we use for wavelength. It's the Greek symbol lambda. Spelled just like that, lambda. And it's kind of weird. You see how it looks? Kind of looks like a weird L. This is to the 14th. This is 3.8 times 10 to the, this is 3 times 10 to the 8. This is 4.29. What this does is this gives us the wavelength in meters, right? You understand? Well, we want it in nanometers, so what we do is we take the meters and multiply it times 9. So it's going to be a fraction. Just like you would do when you was in, or we could take the answer and move it to the left. So let's see what the wavelength this guy would be. If I would do what? I'd say 3, sorry, I usually turn my touch screen off. So it's 3 times 10 to the 8 divided by 7.5 times 10 to the 14th, and I'd equal, and then I'd multiply that times 10 raised to the 9th power. So that would be 400 nanometers. So the higher the frequency, the shorter the wavelength, right? Does that make sense? So we wouldn't be able to see that line. Or it says we would. That would be up towards your ultraviolet. So the shorter the wavelength, you start moving toward ultraviolet. And you start moving toward microwave too. So anything above ultraviolet would be considered microwave. But I don't know exactly where microwave starts. And y'all know what we do with microwaves, don't you? What do we do with microwave? We send information because microwaves, anytime I send out low frequency, it has a tendency to spread out. The higher the frequency, the more it starts acting like light. So we use microwave to send information over long distances and we point to things. So microwave is real hard to intercept. because it's like light. So you see these big microwave towers up on top of hills where they literally beam microwave up to it and they shoot it out the other side. So to intercept it, they would literally have to get up inside the wall, inside the beam. But what else do we do with microwaves? I got an oven in my house called microwave oven. What's a microwave oven do? It causes things to vibrate so much at such a high frequency, then it creates so much friction. What does it do? Heat stuff, cooks it up. So ultraviolet, this is why ultraviolet does what to you. So you put this sunscreen and everything on when you're at the beach. What are you blocking out? You're not blocking out infrared, you're blocking out what? Ultraviolet. Because what will ultraviolet do? It'll cook you. Yeah. Just like you're. And that's about all we'll talk about here. So this is the way fiber works right here. It works off of something called total internal reflection. So what we do is we have what we refer to as a core, and then surrounding it we have what we call a cladding. So this right here would represent what we call a cladding, and this guy right here would be what we call a core. And what these things do is they have different what we call index of refraction, which means light moves at different speeds. So this is like this. I'm over here. If I get below what they call the critical angle, then I can see into the water. But when I get away from the critical angle, I get out here, what does the water do? It reflects it, right? You understand? So look at this. And I've seen pictures of out there in Colorado where the mountains look upside down. They'll show the mountains up here, and the mountains will be down here because we're above that critical angle. If we get above the critical angle on two surfaces that have different refraction indexes, then you will get total. We call this total internal reflection. So that means if I choose this right, and I shoot a beam down through here, and it hits right there, what's it going to do? It's not going to go through here. It's going to do what? It's going to bounce back. And it's going to bounce back. And it's going to bounce back. So now what we're doing is we're shooting a light beam down. This is basically the way fiber optic is. Now we do some things to make it a little better. We can start making the core really thin, and the closer we get it, the faster it's going to go. So we have what we call single mode cable we'll look at, which is basically uses like a 10 to 9 nanometer core. Basically, this is so small that the little bounce down there you can't even detect. And then we have what we call multi-mode, which has a bigger core, usually around 250 nanometers. And now it'll bounce down the side, but the single mode cable is a lot more expensive than the multi-mode cable. Well, that's not true. We'll have to look at it. And that's the way fiber works. They do this with water. You ever see them shoot the light through the water fountain? Well, what they're doing is they got that, as long as they can shoot that water out at such an angle where the light does not, where that angle does not go past that critical angle. If we go past the critical angle, we get refraction. If we stay below the critical angle, we get total internal reflection. So they'll shoot that water out in a nice arc. It's really beautiful. And they'll shoot light through that. So what they're doing is the water has a certain refraction index. The air has a certain refraction index. And as long as that water shoots in an arc, that light will follow what? It'll follow that water stream perfectly, which is pretty neat. Are we okay? Any questions? So this is the first chapter, inside copper. After that, we'll start looking at the actual conductor itself. Have any question on it? Yes, no? Huh? Yeah, I probably will make this one due next Thursday. Is that okay? Make the other one due on Tuesday, make this one due on Thursday. Okay?
Come on.
No, quizzes. That's still not right. I don't know how long the electrical ones are. The electrical ones shouldn't give y'all any problem. Huh? Yeah. So could y'all do the electrical one before Tuesday and do this one before Thursday? Y'all think? Charles said, I'm gonna call them and tell them to take your word. So we okay? Go ahead. No, it doesn't transmit power. And so we can't transmit power with fiber optic cable. Copper so that's one of the big advantages of copper. We can not only use copper to transfer power, or we can use it to transfer information. We can modulate the information and use it to carry both. So your phone system is a perfect example. So those two wires, so even though you run 4 wires, there's only 2 wires that's used by your house phone, if you got a house phone, without a cell phone. And I think they're red and green. Those things carry both the power that powers your phone up, and it also carries the signal. And we can do that because they modulate the signal and make it run at a frequency. Out of U.S. Steel, we had a bunch of the cranes that actually, their communication system, instead of running these cables, actually ran through the power rails of the crane. And they just stripped it off. It's pretty easy to do, to take AC and strip it off of DC. So I can use a device called a capacitor. A capacitor blocks DC and passes AC. So that's all they did is they had a capacitor that their microphone went through, and it went onto the hot rail, and then they transmitted it through the rail. And on the other side, they had another capacitor that stripped off the DC and let them bring it in there. It's a very simple system. But what it does, it allows them to so we can run into electrical conductors that may be carrying both watt at the same time. Maybe carrying power and signal. And the phone system the wired phone system is a perfect example. And even if you get your phone, even if you use voice over IP and you go back to a regular phone, your modem that you hook that sucker up in has to provide power for the phone. So it's doing the same thing. Of course, y'all all know what voice over IP is. Charleston. Voice over IP, so when we send information on these guys, everything's assigned what we call a soft or logical address. We call it an IP address. So anything on an Ethernet network has to have an IP. Well, if I want to use, but it's sent in packets. So we can put voice inside of one of those IP packets, just like we put information you get from any place. So we used to have wires running all these offices. We had wires running everywhere for our phone system, and we had wires running everywhere for our network. Well, see, now our phone system is voice over IP. So I've got one cable coming for the network. It plugs into my phone, and it also plugs into my computer. But what I'm doing, instead of sending digital information over those packets, I'm doing what? Transmitting voice. And that's called voice over IP. Huh? You lose your internet, you use your phone. That's a fact. Believe me. We had the guys out there, Alabama Power in my neighborhood is trimming the trees. Do they ever come to y'all's neighborhood and do that? It's a mess. And a guy was a bucket truck. That thing must have had a 700 foot extension I ever seen. And he was up there cutting something. We heard something go boom, boom, boom. And down he hit one of the high tension wires. And we lost our cable. And when we lost our cable, we lost our wire. Our phone. So we have voice over IP on our station. Yeah, so now what that means is you send voice over the same network that you access your internet through. That's what voice over IP. So now instead of having all these cables running all over the place, we use one cable for both the network and we use the same cable for the phone. So if you went in and looked at my phone in my office, it's got a network cable plugged in. But if your house has a voice over IP, what you do is you just use your phone wiring, and then your modem converts it over to the old phone system type system. Are we okay? All right, guys. See y'all next week. I'll be with you. Total internal reflection. Well, first of all, you have to have you have your EE key, right, or whatever. Okay, so that's your times 10, and then you gotta find your Y to the X key. You gotta square. This is probably is that I guess that's it right there. You can raise it to your power. So what we would do is we started out. Let me go to the frequency. So we started out by saying this one. So we'd say 3, right, times 10 to the 8. Okay. And then we would say divided by our frequency. So we did this one first. I say 4.29 times 10 to the 14. And then I want to make my calculator calculate that. So I'm going to say, okay. We're still okay. We can do it later. And then what I would do is I would take my answer and then I would say times, right? So that's the answer. And then I would say times 10. Now this is where I'm going to use this. Raised to the 9th power. Okay. So that's not times, that's not like we've been doing. Yeah, it's not
engineer notation. It's not engineer notation.
Well, what we're doing is we're converting the number into engineer notation.
Oh.
So it's just like when if you've got this number right here. So let's say I got this number right here. Well, what we say is, how do you get that? You're not using this key times 10 raised to some power. You're saying I'm gonna move this over 1, 2, 3, 4, 5, 6, which is the same as multiplying it times 10 to the 6. Right? You understand? And that's what we're doing. So what we're doing is we're taking this number and we're shifting it over 9 times, but we're not doing it in our head. We're just multiplying it by this number. Understand?
Yeah.
So I could take that number right there. So I could say 0.0. Let's clear this. So I could say 0.000136, and then I could say times 10 raised to the 6th power, and then it comes in 136. But then we would say what? Then we would say micro. Okay. So that's all we're doing is we're doing this right there, right? You understand? But I can't use the exponent key, right? Because an exponent key wouldn't multiply it times 10. It would raise it. It's hard to say. It would.
Usually Y, right? He's used Y.
Well, he don't have a Y to X. He has an X. He has an X to the top.
Yeah.
So this is his raise any number to any exponent. That's yours raised. Yeah.
But mine is the X.
Yeah. See his little guy right there. He's got the little block right there. Does that make sense?
Yeah, it makes sense.
So we can use this key for everything else, because what we're doing is we're going from engineer notation back to the actual number. Here what we're doing is we're taking the actual number and going to engineer notation. So to take the actual number, you have to multiply this number. You have to multiply it yourself, right? You understand? Does that make sense?
Yeah.
Because I can't take an answer and multiply it times and use my EE key. That makes sense? Understand? So I can do this. I can say 23 times 10 to the 3rd, and I hit that, right? You understand? But I can't take the answer. I can't take this answer right here. There's my answer. I can't take my answer and say times 10 to it.
Yeah.
See, because it just leaves it blank. Understand?
Yeah, I get it.
So what we're doing is we're getting the answer, and I can't take the answer and use my EE key with the answer. I can use my EE key to convert a number into engineer notation, but I can't take an answer and convert it. Right? Understand?
Yeah.
So that's why when we get the answer of this, so when we hit that equal right there, that's why we gotta shift, that's why we gotta go to that key, right? Understand? So you understand it now, but you was doing the E, you was using the E key, so you was trying to transfer a number that you keyed in into engineer notation. Instead of the answer, you can't do that. So that key is used when you enter a number, right? Dwayne? Yeah. So I guess those other two guys are not going to show up. I think one of them's paid. Both of them's paid. Couldn't think about it. I think they pay. Because usually if I go to a roll and it's got a little asterisk up there, it means that they haven't paid their tuition yet. I didn't see